topics is related to bioprocess modeling and simulation, where we are primarily discussing on parameter estimation approach. Till date, we already know the lesson 1 according to this presentation is for simulation versus parameter estimation. We want to distinguish between them, how to set up a problem, and we want to solve using some optimization tool. Will be example in this direction, taking care of one bioprocess model. So let's see, we already know how much extent we differentiate between simulation and parameter estimation. Though we already have clarification on the simulation aspect, how is the parameter estimation a different one? So we are comparing different aspects, particularly the model equations are required, whether parameter values are already known, we need experimental data, we need initial values of the state variable, and how is it simple. So you can see simulation in most of the time, yes, all those things will be required, but of course they don't need any experimental data for simulation. But in case of parameter estimation, you will see there are two aspects which is negative. One is parameter values are already known. No, it is not known. We normally have a guess. We'll start, and finally we'll evaluate the final values. And simplicity, of course it is not, because parameter estimation require repeated round of simulation, verification of the values whether it is matching or not, and finally finding out the optimal parameter estimate. Now how a simulation work, probably we already know. We have some example we have already taken. Just to summarize it up once again, we need some initial values of the variables which are important to us for the model perspective. It may be biomass, it may be substrate, or product concentration. Initial values means at time 0, if you know. Of course, in case of ordinary differential equation, solver is required when you are dealing with dynamic model, but it may not be required if it is not a dynamic model behavior. This solver actually deals with some sets of differential equations, and we have some unknown parameter values, but ideally for simulation the parameter values are known. So the differential equations with known parameter are input to the ODE solver. That means ODE solver will start from the time 0. They know the entire equations, parameter values are known, so for every time span it will solve it, and it will solve actually in numerical approach, and we will have all the time versus the state variable values as a solution. So finally we'll have a solution vector, maybe time, biomass, substrate, or maybe as per the requirement we can have the solution vector. So until this it was a simulation, and when we are doing parameter estimation, the same structure will be utilized. It will be already there, but some interaction will be there with a optimization tool, rather, or optimization algorithm. It will interact with the simulation in some two different node. So when you are doing for parameter estimation approach, we need to give actually the algorithm for optimization will have a guess values. So initially you need to provide a guess value for parameter, and once you provide the guess value, the whole procedure as you have seen in simulation will be completed. It will come until the solution. Once it approach the solution, we will compare with the experimental data, because for parameter estimation we need to have real experimental data. Then once we have the solution and experimental, the algorithm will also compare them. How is the difference between experimental and model values? We'll find out their square error for each of the state variable, experimental versus model. The difference will make the square difference, we will sum up. So that is actually sum of square error for each of the state variable probably, and we will see whether the error is very small or still large. If it is in case, for example, the error is not significantly lowered, or maybe still gap is high, then the algorithm, actually optimization algorithm, will say we need to give a new guess values. Of course, the guess value what is providing, it is also having some boundary that will be discussed later. So essentially the whole cycle will repeat. We will have a new guess value. For a new guess value, it will have a new solution. Experimental data remain unchanged. It will compare, it will find out the square error and check whether square error is decreasing or not. So once the square error stop improving further, then we will say error is really very small. Then the algorithm is complete and we found out what is the ideal parameter set to have the minimum square error. That is the algorithm. So apart from the simulation domain, the right hand side all portions is actually coming from one optimization algorithm. So once we know these aspects, we need to know some optimization function also, which will do the job what we are expecting here. Primarily, what is the expectation? It will take some initial parameter guess. So any optimization algorithm will need some guess values that we have to provide, and some constraint. Constraint means the final solution for those unknown things. Is there any limitations? For example, if it is a biologically related or relevant parameters, so we know those values cannot be negative. So for example, specific growth rate or maximum specific growth rate, Kas, monod constant, those things can never be negative. So we can say the maximum value is, for example, plus infinity and minimum value is 0. So we can have some constraint as it required. Then it will have those guess parameter will be provided to simulate the response as we have shown in our earlier slide. Then they will compare. Error will be the objective function of the optimization tool. So optimization tool always need what it is going to minimize. So it will always try to minimize the output of the objective function, and in this process the solution will be projected. So that thing is there. And finally, optimization tool will provide some new sets of parameter, and the whole cycle will continue until or unless satisfactory result is ascertained here. Now this slide will be a little bit theoretical, because we need to know how the optimization things will come into picture. So essentially in this class we will be using Matlab function fmincon, that is actually function minimization under constraint. Constraint means it can be a linearity constraint, non-linearity constraint, or maybe boundary, upper boundary, lower boundary, like that. So essentially the function syntax, if it is, we are going to show you the fun is the function which will actually calculate the square error. X0 is the initial value, so one time we need to provide what is the starting value, guess value for your parameter. A and B are actually can be a matrix or vector for linear inequalities. So for example, somewhere you know that some constant into your unknown values, for example x1, x2 are the two unknown values, if it is somehow related with another variables, so that can be given some linear inequalities constraint. Similarly, we can have sometime linear equality constraint. Anyway, we will not discuss it here at this moment. And finally, lower boundary and upper boundary. So for example, if we know our x0 is two parameters are there in our x0, so lower boundary will also be a row vector of two values. So lower boundary for first parameter, lower boundary for second parameter, and ub will be upper boundary for first and second parameter. Non-call is a non-linear constraint. If you anything have, we will not discuss here now. And option for optimization, and that we'll be discussing later, not at this moment. If we are not using anything, then we will put it as empty bracket for any of the constant if you are not going to use. Now we'll take one example very carefully. Let's see how we are using the fmincon function. We'll be showing you one Matlab file also very soon. Now assume this is really very simple and simple regression actually, that is biomass concentration and optical density values are given. For example, x values are 0.05, 0.09 and so on. that is for optical density, and for example y, some protein concentration or biomass concentration is given, for example 1 2 4 6 7 10 like this, and we want to find out if there is any linear relationship is there. That means we are putting a model that is y equal to mx plus c. Of course this is the model we want to find out. So we know what is our expected equation, but we don't know what is the value for m and c. Of course you can do in a Excel, you can make a plot and find out what is the slope and intercept. That is different aspect, but we're going to use it using our Matlab. How can we use it? We will assume this is our model equations. So we do have two parameters to find out. Parameter means unknown constant things. M is the slope and C is the intercept. We don't know. So we have to start from a guess for M and C. We have to try to find out what is the model values based on those guess value for M and C. So in this case, if we know that okay, X is our going to be independent variable, so Y is our dependent variable, so we will try to find out what is the model Y based on the equation mx plus c, but we already know what is the actual Y. So the actual Y values will be comparing with the model to see how is their difference or how is the error. We'll try to find out the square error is as small as possible. That will be our objective anyway. So here I'll be showing you, not this slide, rather we'll try to show a different aspect in our Matlab file itself, but now this file you are not opening. You can see we are talking about similarly function reg. This syntax you already know: clear, CLC, format sort G, format compact, all those things are already known to you. So here I am assuming x equal to those values as a column vector. We are taking y actual values 1 2 4 6 7 10 that we already know, and we are putting those x and y value together. So we are making a matrix of x and y actual. That is our data. Of course this is our experimental data, we know this. Now we'll come into our fmincon function here. Before that we need to tell what is the lower boundary and upper boundary, because we know there are two unknown things. So the max m and c, I am assuming the guess value initially as 1 1 is the guess value. The lower boundary I am assuming minus infinity because this is a linear equation, it can have minus values also, and upper limit is plus infinity. So lower and upper boundary we are putting. So now option we will not discuss at this moment, we are taking it out, and guess value, initial values I am putting 1 1. So this is initial values, lower boundary within which our m and c value. For minus infinity this is for m, this is for c lower, and this is upper plus infinity. Now coming into our expression for fmincon, you see we are calling fmincon. We are giving a function which will be actually minimized, that we will discuss later, coming soon. We are using the guess value that is actually 1 comma 1. These linear, non-linear constants are not used, so we are keeping it as empty bracket. Lower boundary and upper boundary, as we already know, minus infinity, plus infinity, we are writing it here. Non-linear constants are not utilized. Options we are already telling large scale data algorithm will be interior point. These aspects we will be discussing later, not at this moment. And data means this x and y values, composite whole things we are providing. That means fmincon will evaluate the function name is minfun. Its initial value is guess, the parameter value is guess, and these are the lower and upper boundary, and this is the data which will be required to calculate your minimum using function. So now you see this is the function for minimum. So function SSE, that means SSE is the output of this function. So the algorithm will try to minimize SSE value. What is the SSE value? We will come to know very soon. So function name same, minfun is the function name. It is input output is para. Para will be provided by the fmincon function. Initial para is actually guess values, that is 1 1, and the data we are already getting from this one. Not necessarily we need to give the same variable name, we can give any other variable name, but it is being passed from fmincon itself. So we know para maybe, for example, first time it is 1 1, and we know the data. So m is actually para 1 because there are two sets of para, m, and c is our para 2. X, now data contents are experimental data, so the first column is actually x and second column is actually y, that is experimental one. Then using the model, because I know what is m value and what is c value at any time, so I can calculate the model data, that is m multiplied x plus c. So m is actually scalar value, c is scalar value. So this evaluation will be done multiple times. For one time, for example, in the very beginning it is 1 1 m1 c1, then they are calculating y model, and then we are calculating error, that is y model minus y actual. We are making the square error, we are calculating sum. So sum is the output. So once this we are, and what is the output for fmincon function, that is the final para, that is para out the final values of the parameter for which the sum of square is minimum, because fmincon is going to minimize the output of the min function. Like here output is SSE, so it is going to minimize SSE by changing those parameter value starting with guess, and data is of course required, so SSE will be minimum. So that is fval is the evaluated values, that is the minimum SSE, and para op is the corresponding parameter values which is optimized. So this can be used to find out the solutions based on here. We'll discuss it later in the next